Look at your hand right now. Meta. Sex. 1.0. Seems solid, right? Real. Physical. Made of atoms. But those aren't little balls you're looking at. What you think you're seeing doesn't exist. That picture of the atom you learned in school. Nucleus in the center. Electrons orbiting around it like tiny planets around a little sun. That model is wrong. Not a little bit wrong. Completely, utterly, fundamentally wrong. And I'm warning you now, you're not going to like what I'm about to tell you. Because what's actually inside an atom is so strange, so contrary to common sense, that your brain is going to fight me every step of the way. But once you see it, you can never unsee it. Let me show you what's really there. Let's start with the simplest atom there is. #meta. Pause. Sex. 1.0. Hydrogen. One proton in the center, one electron somewhere around it. That's it. The atom everyone uses to explain things because it's supposed to be simple. So here's a simple question. Where exactly is the electron? You want to point and say, it's over there, on the left side of the atom, moving in a circle. Wrong. The electron is not over there. The electron doesn't have a definite position. Not because we can't measure it precisely, not because our instruments aren't good enough. The electron itself doesn't have a definite location until you measure it. This is not philosophy. This is not interpretation. This is what the math says. This is what experiments confirm over and over and over again. The electron exists in what we call a superposition. It's not here or there. It's here and there, simultaneously, in multiple places at once. Now you're thinking, okay, fine. So the electron is spread out like butter on toast, distributed thinly over a region of space. No, that's still wrong. The electron is not spread out. The electron is a point particle when you measure it. But before you measure it, it doesn't have a position. What's spread out is the probability of finding it. There's something called a wave function. It tells you where you're likely to find the electron if you look. In some places, the probability is high. In other places, it's low. In some places, it's 0. You will never, ever find the electron there. But here's the thing that breaks your brain. Before you look, the electron isn't hiding in one of those high probability spots. It's not secretly over there and you just don't know where. It genuinely doesn't have a location. The wave function is the electron. That's all there is. There's nothing more fundamental hiding underneath. Think about that for a second. The most basic building block of matter, the electron, doesn't exist in a definite place. It exists as a cloud of possibilities. A mathematical object that describes what might happen when you look. And this isn't some weird edge case. This is the foundation. This is what everything else is built on. In the solar system picture, the electron orbits the nucleus like a planet orbiting the sun. Round and round, a nice circular path. But here's the problem. Orbiting means accelerating. Anything moving in a circle is accelerating, even if its speed stays constant. Because its direction is constantly changing. And accelerating charged particles radiate energy. They emit light. That's basic electromagnetism. We can measure it. It happens. So if the electron were really orbiting, it would be constantly losing energy, radiating it away as electromagnetic waves. And as it loses energy, the orbit would shrink. The electron would spiral inward, closer and closer to the nucleus, faster and faster, until, crash, it hits the proton. The atom collapses. How long would this take? Do the calculation. It takes about 10 to the minus 11 seconds. That's 100 trillionth of a second, about 100 picoseconds. Every atom in the universe should collapse instantly. Obviously, that doesn't happen. Atoms are stable. They don't collapse. You exist. I exist. The chair you're sitting on exists. So the electron can't be orbiting. Okay, you say. So maybe it's not orbiting in a circle. Maybe the electron is just sitting there, stationary, held in place by the electric attraction to the nucleus. Also wrong. Because if the electron was sitting still, we would know both its position and its momentum exactly. Position, right there. Momentum, 0. And quantum mechanics says you can't know both of those things exactly at the same time. That's the Heisenberg uncertainty principle. It's not a limitation of our measurements. It's not that our instruments aren't precise enough. It's a fundamental property of nature. If you try to pin down the electron's position perfectly, its momentum becomes completely uncertain. It could be moving at any speed, in any direction. If you try to pin down its momentum, its position becomes uncertain. It could be anywhere. You can't have both. So the electron is not orbiting. Because orbiting atoms would collapse in a trillionth of a second. And the electron is not sitting still. Because sitting still violates the uncertainty principle. What is it doing? It's not doing anything. It just is. The electron exists as a wave function, a mathematical description of probabilities. It's not moving in a path. It's not sitting in a location. It exists as a cloud of might be here spread around the nucleus. And that wave function has certain allowed shapes, certain allowed energies. We call these shapes orbitals. An orbital is not an orbit. It's not a path the electron travels. It's a region of space where the electron is likely to be found, described by the wave function. The simplest orbital, the ground state of hydrogen, is spherically symmetric. The probability is highest right at the nucleus and falls off gradually as you move away. There's no orbit, no path, just a fuzzy cloud of might be here. Higher energy orbitals have stranger shapes. Some look like dumbbells. Some look like donuts. Some have multiple lobes pointing in different directions. These aren't physical objects. They're probability distributions, maps of where you might find the electron if you look. So when your teacher drew that picture of electrons orbiting the nucleus like planets around the sun, it wasn't a simplification. It wasn't close enough. It was wrong. Fundamentally, completely wrong. In a way that hides the actual strangeness of what's really going on. Atoms don't work like solar systems. They work like nothing you've ever experienced. Nothing in your everyday life prepares you for this. And we're just getting started. So the electron isn't orbiting. It isn't sitting still. It just is. But what does that actually look like? We call these shapes orbitals, not orbits, orbitals. An orbital is not a path. It's not a trajectory the electron follows. It's a probability distribution, a map of where you're likely to find the electron if you look. The simplest orbital, the ground state of hydrogen, is spherically symmetric. A fuzzy ball of probability centered on the nucleus. The electron is most likely to be found right at the nucleus, less likely farther away. But there's no orbit, no path, just a cloud of might be here. Higher energy orbitals get stranger. Some look like dumbbells, two lobes pointing in opposite directions. Some look like donuts, ring-shaped probability clouds. Some have 4 lobes, 6 lobes, 8 lobes, pointing in different directions like a 3-dimensional flower. These aren't physical objects. They're solutions to the Schrödinger equation, mathematical descriptions of where the electron might be. And here's where it gets really weird. When an atom absorbs or emits energy, the electron jumps from one orbital to another. We call this a quantum leap. One moment, the electron's wave function is in the shape of the lower orbital. The next moment, it's in the shape of the higher orbital. No in-between, no smooth transition. The electron doesn't travel through the space separating the two orbitals. It just appears. Think about that for a second. How does the electron get from here to there without passing through the middle? We don't know. The math describes it. The experiments confirm it. Every spectroscopy measurement in every lab in the world shows these instantaneous transitions. But there's no mechanism. There's no video of the electron traveling. There's no explanation for how it happens. It just does. This bothers physicists. It should bother you, too. We've been doing quantum mechanics for a century, and we still don't know how quantum leaps work. But the math is right. The predictions match to extraordinary precision. So we keep using it, even though we don't understand the mechanism. Welcome to quantum mechanics. Where we don't know is an honest answer, not an evasion. Is an electron a particle or a wave? You learned it's a particle, a tiny ball with mass and charge. Maybe very small, but still a thing, an object. Except when we do experiments, the electron also behaves like a wave. It can interfere with itself, pass through two slits simultaneously, spread out and recombine. All the things waves do. So which is it, particle or wave? Neither. The electron is not a particle. It's not a wave. It's a quantum object, something that doesn't have a classical analogy, something that exhibits particle-like behavior in some experiments and wave-like behavior in others. When you're not looking at it, the electron is described by a wave function. That wave function evolves smoothly, spreading out, interfering with itself, doing all the things waves do. But when you measure the electron, when you actually detect it, you always find a localized particle, a dot on a screen, a click in a detector, never a smeared-out wave. The act of measurement collapses the wave function. The spread-out probability cloud instantly becomes a definite outcome. Here, not there. One spot. This is called the measurement problem. And nobody knows how it happens. Nobody knows what counts as a measurement. Does it require consciousness? Does it require a machine? Does a rock making a measurement count? Nobody knows. Remember the Matrix? There is no spoon. Turns out the movie got it backward. The spoon is the only thing that exists, as a pattern of quantum fields. The question is, who's observing it? What counts as an observer? There are interpretations. Many worlds says every measurement splits the universe. Pilot wave theory says there are particles guided by the wave function. Copenhagen says shut up and calculate. But these are interpretations, not explanations. We don't have a consensus. The measurement problem has been bothering physicists for nearly a century. Here's what we do know. Before measurement, the electron is described by a wave function, a superposition of possibilities. After measurement, the electron is in a definite state, one of those possibilities. The measurement doesn't reveal a pre-existing reality. It creates a definite reality from a fuzzy one. You can't passively observe at the quantum level. The act of looking changes what's there. This is why we can't say where the electron is before we measure it. Not because it's hiding, not because we're not good enough at measuring. Because the property of being in a definite location doesn't exist until we perform a measurement that creates that property. The electron isn't somewhere, waiting for us to find it. The electron is everywhere and nowhere until we look. And then it's somewhere specific. How? We don't know. Why? We don't know. But the math works. The predictions match experiments. That's all we have. So we've talked about one electron. Hydrogen. Simple. Now let's add more. Helium has 2 electrons. Lithium has 3. Carbon has 6. Iron has 26. Uranium has 92. All these electrons exist simultaneously as wave functions around the nucleus. But here's something that should bother you. The electrons are identical. Not similar. Not nearly the same. Identical. Electron number 1 and electron number 2 are not 2 different things that happen to have the same properties. They are the same thing. The same entity appearing in multiple places. Think about that. In the macroscopic world, no 2 things are ever truly identical. Even 2 golf balls have microscopic differences, different atoms in slightly different positions. But electrons? No differences. None. 0. Fundamentally, absolutely identical. This has consequences. In 1925, Wolfgang Pauli discovered something strange. When you swap 2 electrons, the wave function of the entire system changes sign. It picks up a negative factor. This isn't a detail. This is fundamental. We call it the Pauli exclusion principle. No 2 electrons can occupy the same quantum state. If one electron is in a particular orbital with a particular spin, no other electron can be in that exact same state. They have to stack up, filling different orbitals, building structure. Now here's where it gets personal. Look at your hand again. Right now, every atom in your body is a pattern of probability. The electrons in your skin don't have definite positions. They're probability clouds, described by wave functions, existing in superpositions. You're held together not by solid stuff, but by the Pauli exclusion principle, a mathematical rule that says no 2 electrons can be the same. Remove that rule, you'd fall through the floor. Actually, there would be no floor to fall through. Without the exclusion principle, all electrons would collapse into the lowest energy state. Every atom would be chemically identical. No complexity, no molecules, no chemistry, no you. This is the reason matter is solid, the reason you don't fall through your chair, the reason atoms have structure, the reason chemistry works, the reason life is possible. One mathematical rule holding together everything that exists. But why? Why does swapping identical particles change the sign of the wave function? We don't know. It's just the rule we discovered. The math works. The experiments agree. But there's no deeper explanation. Welcome to quantum mechanics, where some questions don't have answers because the questions themselves assume a reality that doesn't exist. You probably think the nucleus is simple. A bunch of protons and neutrons packed together. Little balls stuck to each other like marbles in a bag. Wrong. Again. Protons and neutrons are not fundamental particles. They're made of quarks. 3 quarks each, up quarks and down quarks, held together by particles called gluons. But the quarks don't just sit there like marbles in a bag. They're quantum fields. Fluctuating, interacting, constantly exchanging gluons. The proton isn't a container holding 3 quarks. The proton is a bound state of the quark field, a stable pattern of oscillation. And here's the really strange part. Most of the mass of the proton doesn't come from the quarks themselves. The quarks are nearly massless. They contribute maybe 1% of the proton's total mass. Where does the other 99% come from? Energy. The gluon field holding the quarks together carries enormous energy. And energy equals mass. E equals mc squared. That's not just a formula. That's reality. So when you step on a scale, what are you weighing? Not stuff. Not particles. Not solid matter. Energy. Bound field energy arranged in stable patterns. Most of your body's mass comes from the energy of gluon fields inside protons and neutrons. You're not made of stuff, you're made of energy. And the strong force holding protons and neutrons together in the nucleus? It's mediated by particles called pions. But pions are also made of quarks, quark-antiquark pairs, which are excitations of the quark field. It's quantum fields all the way down. There is no bottom, no solid foundation, no ultimate building blocks that everything else is made of. Just fields, patterns, energy, math. So if it's not particles at the bottom, what is it? Fields. Quantum fields. The electron is not a tiny ball. The electron is an excitation of the electron field, a vibration, a ripple in something that permeates all of space. The quarks inside protons? Excitations of quark fields. The gluons holding them together? Excitations of gluon fields. It's fields all the way down. And what is a field? A mathematical object. Numbers assigned to every point in space. That's it. Numbers. You want there to be something real at the bottom, something you can touch, something solid, something that explains everything else. There isn't. There's just math. The atom is not a thing. It's a pattern, a stable configuration of field excitations, a mathematical structure that persists through time. Think about that for a second. The chair you're sitting on? A pattern of patterns of patterns. Molecules made of atoms, made of quarks, made of field excitations. At no level do you find stuff. At every level, you find math. This is the deepest truth about what atoms really are. Not little balls, not tiny solar systems, not even particles in any meaningful sense. Patterns in quantum fields described by equations. Now let me show you how fundamental this is. Imagine atoms stopped existing for 1 second. Not vanished, just the patterns in quantum fields flickered out. The excitations went flat. The math stopped being solved. You wouldn't see anything change. You would be the change. Every molecule in your body would dissolve, not into pieces, into nothing. The chair you're sitting on? Gone. The floor beneath you? Gone. The air you're breathing? Gone. Because there's nothing to dissolve into. Without these quantum patterns, there is no matter. There are no objects. There is no structure. The patterns are reality. That's what atoms really are. Not little balls you can stack like Lego. Not building blocks of nature. They're the math that makes reality possible. Without the patterns, there's just empty field. Featureless. Structureless. Nothing. And you are made of these patterns. Right now. Every thought you're having is a pattern of patterns. Every sensation you feel. Every memory you have. Patterns in quantum fields. Math. That's all you are. If that doesn't change how you see yourself, nothing will. You've heard atoms are mostly empty space. That's wrong, too. The space between the nucleus and the electron shell isn't empty. Quantum fields are there. Virtual particles pop in and out of existence constantly. The vacuum is seething with activity. Here's a number that might help. If the nucleus were the size of a marble, the atom would be the size of a football stadium. That's about 100,000 times larger. The ratio is staggering. But here's what's weird. The electron has no size. 0 dimensions. A mathematical point. As far as any experiment has ever measured, the electron is infinitely small. How does something with no size take up space? How does a point particle create a probability cloud that spans an entire atom? We don't know. It just does. And then there's spin. Electrons have spin. You might picture a tiny ball rotating on its axis, like Earth spinning. Wrong. Spin is intrinsic angular momentum that doesn't come from rotation. The electron isn't spinning, it just has spin as a fundamental property, like charge, like mass. And here's the strange part. Electron spin is exactly 1/2, in units of Planck's constant divided by 2 pi. Not approximately 1/2, exactly 1/2. How can angular momentum be quantized to exact fractions? Why 1/2 and not some other number? We don't know. It's just how spin works. Nothing in your everyday experience behaves this way. Nothing you've ever touched or seen or felt operates by these rules. Your intuition was built for the macroscopic world, rocks and trees and animals, things that follow classical physics. Atoms don't care about your intuition. They operate by rules so foreign, so alien to your experience, that the best you can do is accept the math and watch your common sense surrender. That's quantum mechanics. That's what's really inside atoms. So how do we know any of this is true? Here's the thing that should convince you. The predictions match experiments to extraordinary precision. Not close, not approximately, precisely. We're talking 10, 12, sometimes 14 decimal places of agreement between theory and measurement. That's like predicting the distance from New York to Los Angeles and being accurate to within the width of a human hair. That's about 0.003 inches, or roughly 0.08 millimeters. Quantum electrodynamics, the theory Feynman helped develop, is the most precisely tested theory in all of science. So the theory works. But here's the uncomfortable part. Nobody knows why it works. Energy levels in atoms are quantized, discrete, like notes on a guitar string. You can have this frequency or that frequency, but nothing in between. You can't play half a note. Why? Why does energy come in discrete chunks instead of continuous values? There's no deeper reason. It's just how quantum mechanics works. We can describe it, we can calculate it, we can predict it with insane accuracy. But we can't explain it in terms of anything simpler. And here's the deepest weirdness of all. Measurement doesn't reveal a pre-existing reality. It creates a definite reality from a fuzzy one. Think about what that means. Before you look at an electron, it doesn't have a definite position. It's not hiding somewhere, waiting for you to find it. The property of being in a definite location doesn't exist until you measure it. The measurement creates that property. You can't passively observe at the quantum level. The act of looking changes what's there. Some physicists find this disturbing. Einstein famously said, "God does not play dice with the universe. He was wrong. The universe plays dice all the time. Every quantum measurement is fundamentally random. You can calculate probabilities. You can never predict exact outcomes. This isn't a limitation of our knowledge. It's not that we're missing some hidden variable that would make it deterministic. Bell's theorem and experiments since the 1970s have proven the randomness is real, fundamental, built into the structure of reality. And yet the statistics work. The math works. The predictions match to 14 decimal places. We can't explain why. We can only describe what. That's quantum mechanics, the most successful and the most mysterious theory we've ever created. So what's really inside an atom? Not little balls, not orbits, not stuff. What's inside an atom is a mathematical structure, a wave function, a solution to the Schrödinger equation. The wave function doesn't live in regular space. It lives in something called Hilbert space, a mathematical space with potentially infinite dimensions. It's information, not substance. Patterns, not particles. Math, not matter. Remember what we started with? Look at your hand again. Those atoms you're made of? They're not tiny solar systems. They're not solid building blocks. They're stable patterns in quantum fields. Mathematical structures that somehow persist through time. And here's what should fill you with wonder. From this incomprehensible math, you emerged. Consciousness looking at the equations that created it. Patterns in quantum fields asking what patterns in quantum fields are. If that doesn't fill you with wonder, nothing will. This is what's really inside an atom. Not particles, not stuff, but math. Pure, abstract, beautiful, incomprehensible math. And the universe doesn't care what you want. It doesn't care what makes sense to your monkey brain. It doesn't care if you find this disturbing or confusing or impossible to picture. It is what it is. And what it is far stranger than you ever imagined. If this changed how you see reality, even a little bit, drop a comment below. Tell me which part broke your brain the most. Subscribe if you want more physics explained the way Feynman would have explained it. No memorization, just understanding. And I'll see you in the next one.